All right, guys, picking up where we left off. This is part 2, video 2. I believe we're starting on question number 7. So they want us to solve this one. It says, please use a graphing device to find the solution so you could use it to find others. So like always, carefully type this in. Not the equal 0, just this right here. Type that into Desmos, and let's see where it crosses the x-axis. I'm pretty sure it might be +1 or -1 or maybe both, but we're going to have to use those answers to find others. But let's check out the graph. So if you type this in correctly, you'll see that this point of intersection is a crazy decimal. That means it's irrational. There's a square root involved. This other one's also a crazy decimal. There's a square root involved. But we do have at least one nice answer. That's x equals 1. Okay, so let's take a look at, by the way, this is a third degree equation, which we want 3 answers, and we actually have them here. It's 1, 2, 3. These are 3 real answers. The problem is we know that these are crazy decimals. They're irrationals, which means that it's a square root of a non-perfect square number. So what are those? Let's take a look at our multiple choice answers again. So we already found out that this is one of the answers, not -1, just +1. And it's going to be, well, it can't be this one because this one's imaginary. The other 2 crazy decimals either came from this one or that one. So how am I going to tackle this? I'm going to take this answer, use synthetic substitution to get a depressed polynomial, which should be a quadratic, which means I'll be able to use a quadratic formula to see which one of these is correct. So we're going to take this one and put it right here inside the box. That's the solution. We're also going to take the coefficients 1, -6, 7, and -2 and make a list. There is no powers missing, so I don't need to fill in any spaces with 0. So there's my list of coefficients. Now we're going to draw my line, and as I go down, I combine. 1 plus nothing is 1. As I go up, I multiply. 1 times 1 is 1. As I go down, I combine. -6 plus 1 is -5. As I go up, I multiply. 1 times -5 is -5. As I go down, 7 take away 5 is 2. As I go up, I multiply. 1 times 2 is 2. And like I said, we always like to see that 0 there because it assures us that we did everything perfectly correct. So we now have a quadratic, 1x squared minus 5x plus 2. Let's write it out. And it would be nice if I could actually factor it, split it, and solve to be able to find my other 2 answers, but we already know that the other answers are irrational. They're crazy decimals. So we know that we're going to have to use the quadratic formula where my a value is 1, my b value is -5. Maybe I should do the b value in blue. And the c value, I'll do it in green, is 2. So let's plug it all into the quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac all divided by 2a. And when we use a quadratic formula, it'd be a great idea to use parentheses. And I'm going to do that up here. So the a value of 1 is going to go down here and up here right next to the -4. The b value of -5 is going to go right here, and the green c value of 2 is going to be over here. So working on our discriminant, the value inside the square root, we have -5 to the 2nd power, that is +25. And then we also have -4 times 1 times 2, that'll be a -8. And again, that's still inside the square root. 25, take away 8, that is 17, I believe. So instead of writing it, let me just write it as a square root of 17 right there. So what else do I have? I have the -5, which became a +5. We have the plus or minus, there it is, plus or minus. And we have 2 times 1, that's 2. So this is what we have so far, 5 plus or minus the square root of 17 over 2. Now, if this could be broken down to a perfect square number, I mean, with multiplication, like let's say it was 12, then you could break it down to 4 times 3, but it's 17. You can't break it down with multiplication to get a perfect square number. 17 is not a perfect square number. So that's as far as we could simplify. So this is right here, your 2 answers. Those crazy decimals that we saw on the graph, it must come from taking the number 5 plus the square root of 17, getting a crazy decimal answer, dividing it by 2, and that'll give us one of those crazy decimals. And then going back and doing 5, take away the square root of 17, which is a crazy decimal, then dividing by 2, and then that would be the other crazy decimal that you see on the graph. So our answers, our 3 answers to this cubic equation are right here. This guy right here and that guy right there. Remember, these are two answers. They're not imaginary, they're real. They're just ugly decimals, and that's where these ugly decimals come from, right? That one and that one. Let's move on. This next question says, write a polynomial function of least degree with integral coefficients that have the given zeros, -3 and 4i. What does it mean that they give you zeros? Remember, zeros, solutions, x-intercepts, they're all the same thing. They're all answers. So they're telling you that one of those answers is -3. So I would go to the bottom of any space on your paper and put x equals -3. And I'll also go over here and say x equals 4i, positive 4i. Now, I hope we remember the complex conjugate theorem that states if you have any complex number, which is an imaginary, then the conjugate of that must also be an answer, right? If you have an answer that's imaginary, then the conjugate of that must also be an answer. So you should also have a -4i right there as an answer. So we have our 3 answers, and that makes total sense because all of these have the power of 3. We just need to work backwards to see which one of these it is. Now, yes, technically you could type this into Desmos and see if it has the x-intercept of -3, types this one in. But even if it has the x equals a -3, the x-intercept of -3, you would still have to take the answer -3, plug it in to see if you get these other imaginaries. So let's not mess with graphing. Let's just work backwards. Where did this answer come from? It came from the binomial. If you add 3 and add 3, it came from the binomial x plus 3 set equal to 0. Right? If you solve that, you're going to get that red answer, x equals -3. Where did this blue answer come from, x equals 4i? Well, let's set it equal to 0. It came from x minus 4i being set equal to 0, right? Maybe I should put this in parentheses as well. And the last one, the x equals -4i, go plus 4i, and that'll tell you the binomial that blue answer came from. It came from x plus 4i being set equal to 0. Okay, so these are each set equal to 0 because if we were working the normal way, zero product property would allow us to split the factored form and set each of those factors equal to 0. So we're going to go backwards and with zero product property put these all together. So the x plus 3 is going to be right here. But the next two I'm going to write in red because the x minus 4i and the x plus 4i are conjugates of each other. And yes, it's still equal to 0. But what we want to do is multiply the complex number with its conjugate first, because we know that when we do multiply by a conjugate, it ends up being a nice, beautiful binomial and the imaginary values disappear. So if you get that, once you do this process so many times, you'll be able to see it like me. I already know that the answer is going to be x squared plus 16. But you'll see that once you do it over and over. Check this out. You're supposed to go x times x, that is x squared. X times 4i, that's positive 4xi. Negative 4i times x is just a negative 4ix or 4xi. Negative 4i times positive 4i, that's a negative 16i squared. And I usually put that I squared in red because you should remember that that I squared is really a -1. So what you really have right here is a negative 16 times -1, which will ultimately be a plus 16. And what about those middle terms? They're exact opposites. One's positive, one's negative. They cancel out. So what we have left is x squared plus 16. That's what we have left, right? I have the x squared and I have the positive 16. That's what I have left. Now I still need to multiply this guy by this other binomial x plus 3. So let's do that. Let's move the x plus 3 up here. And we're going to have to distribute and combine like terms. So I am going to start with x times x squared, that's x to the third. X times 16, that's 16x. And then the positive 3 times x squared, I'll go like this, positive 3 times x squared, that's positive 3x squared. Positive 3 times 16, that's positive 48. And of course, when we write our final answer, we want to write it in standard form from the highest exponent down to the smallest down to the constant. So the highest exponent is x to the third, and then we have plus 3x squared, and then plus 16x, and then the constant plus 48. So when we look at our multiple choice answers for that, the only one that has a 48 is right here, and everything else is perfect. So this one right here is our answer. This next question says, state the rational roots. So what are we talking about? The answers. Rational answers are talking about those real answers, those answers that make sense, that are on the x-axis. So of course, we're going to graph it with Desmos. It says if there's more than one, put a comma between your answers. So if you see that it crosses, well, first of all, the degree 3, it might cross 3 times. Or maybe it just touches at one spot and crosses at another. Maybe have a, the duplicity situation. But let's see what happens. Let's graph it. And if you do graph it and zoom in appropriately, if you look around the whole x-axis, it only crosses right here at x equals -5. So if it is a third degree polynomial, then one answer is -5. The other two must be imaginary. Let's go back to the problem itself. Keep in mind the answer is x equals -5. So looking back at this question, that we already found the answer, the rational root, because rational means that it makes sense, as in, if it would say state all of the solutions, then you're talking about the real and the imaginary. Right here it just says state the rational roots, which means -5, and that's it. Now this question right here, compared to the previous one, says find all the zeros, not just the rational roots. So find all of them. You're talking about the real answers and the imaginary. Type this into Desmos, and you should see that it has the two answers, -2 and +1. Again, x equals -2, x equals +1. So this is an answer and that's an answer, -2 and +1. We're going to use these answers and plug them in with synthetic substitution. So I'm going to take the -2 and I'm going to plug it in, and I'm going to make a list of my coefficients. There's a leading coefficient of 1 on the x to the 4th, a coefficient of 1 on the x to the 3rd, coefficient of 7 on the x squared, of 9 on the x, and a constant of -18 at the very end. And as I go down, I combine. This 1 plus nothing is 1. As I go up, I multiply. -2 times 1 is -2. As I go down, I combine. 1 and -2 is -1. As I go up, I multiply. -2 times -1 is +2. As I go down, I combine. 7 plus 2 is 9. As I go up, I multiply. -2 times 9 is -18. As I go down, I combine. 9 and -18 is -9. As I go up, I multiply. -2 times -9 is +18. And of course, I am happy to see the remainder of 0 because that reassures me that I did everything right. Now, this is a depressed polynomial, but if I started out with the 4, this is a depressed polynomial of x to the 3rd. I would like an x squared. So instead of rewriting this with the x to the 3rd, a -x squared, a +9x, and a -9, I'm going to just keep the list right there and plug in my next answer of +1. I'm going to put it right here, and I'm going to put in this +1 right there, and I am going to do synthetic substitution again. As I go down, I combine. 1 plus nothing is 1. As I go up, I multiply. 1 times 1 is 1. As I go down, I combine. A -1 and a +1 is 0. As I go up, I multiply. 1 times 0 is 0. As I go down, I combine. 9 plus 0 is 9. As I go up, I multiply. 1 times 9 is 9. And once again, I'm happy to see the remainder of 0. Again, now that I've depressed this 4th degree 2 times, now I'm down to a quadratic, and I know quadratics. So this is a constant 9, which is positive. The 0 is a 0x, and we have, of course, a x squared. So we're not going to write the 0x. I'm just going to put x squared, and that's an x squared plus 9. So what does this mean? This is a factor of that. If I wanted to write this whole thing in factored form, okay, well, this answer, -2, came from the binomial x plus 2. So you'd have an x plus 2 in parentheses. This came from x minus 1. You'd have an x minus 1 in parentheses. And of course, you'd have this in parentheses. And that would be in completely factored form. And if it was in factored form, what would you do? You would split them all and set them each equal to 0, and that's how you'd get this answer, that answer. Now we still need to set this equal to 0 and get the final answer here. So I am going to subtract 9, and I will have an x squared equals -9. So I'm going to square root, and square root, I'll have my final answer, x equals plus or minus. Now what is the square root of 9? It's 3, but that negative is going to make it a 3i, okay? Once again, the negative comes out as an I, and the square root of 9 is 3, so I times 3 is 3i, and there is a plus or minus in front of it. So there is your third and fourth answer. Once again, you have 2 real answers to this 4th degree polynomial, and 2 more imaginary. Let's move on. Which polynomial equations did these solutions come from? Well, we need to work backwards here. I know that my answer is x equals -5, and I also have another 2 answers. If the x equals -2i, if x equals -2i, then x must also equal +2i, okay? So we have these 3 answers, and that makes total sense because all these are 3rd degree polynomials. And where did these answers come from? They came from binomials that were set equal to 0. So this first binomial came from x plus 5 that was set equal to 0. Again, if you don't know what I'm doing here, all I did was simply set it equal to 0, and that's how I got the x plus 5, and that's 0. So x plus 5 equals 0. And I usually write these in parentheses. Now, this next one, where did this answer, x equals -2i, come from? It came from x plus 2i set equal to 0. And the last one came from x minus 2i set equal to 0. So at what point in the solving process do you set all of your factors equal to 0? That's when you apply zero product property. So we're going to use zero product property backwards to put these binomials together. And I say begin always with your complex number times your complex conjugate, because we know it ends up being something beautiful. So when I distribute x times x, that's x squared, distribute x times -2i, that's -2xi, or 2ix, and then positive 2i times x is a positive 2xi, or ix, and then positive 2i times -2i, that is a -4, because positive 2 times -2 is -4, and then I times I is I squared, which we know is actually -1. So the middle terms, these guys are complete opposites, those disappear. So what do we have left? We have the x squared out here, and we have a -4 times a -1. -4 times -1 is +4. So this is our binomial answer for multiplying both of these conjugates. You end up with x squared plus 4. So we still need to multiply that x squared plus 4 by this x plus 5. And then that'll be our final polynomial answer. So let's distribute. We're going to begin x times x squared, that's x to the 3rd. We have x times 4, that is 4x. We have 5 times x squared, that's plus 5x squared. And 5 times 4, which is plus 20. Obviously, we'd still need to rearrange it, put the x squared before the x, so switch the 5x squared with the 4x, and you will see that this is the only one that satisfies, well, that's correct. What am I saying satisfies? That's the right answer right there.